In this example problem, we'll be doing a calculation involving both interference and diffraction. We're trying to determine the separation of the two slits of a double slit assembly. And this double slit, the individual slits are each 0.0125 centimeters wide. And as we observe the central pattern of the single slit pattern, in that width there are 9 visible fringes. It turns out in this problem that we have a minimum of the double slit pattern occurring at the same place as the first minimum of the single slit pattern. You may have heard of missing order problems. This is not a missing order. All the orders of the double slit pattern are present. All the orders of the interference pattern are present. So how do we accomplish this? Well, I'd suggest first that you do a drawing. So over on the left side here, I have a drawing of the situation of part of it. Here's the central maximum. I'm going to label that with a 0. And then 1, 2, 3, 4. And then this is the spot where the minimum of the double slit pattern is at the same position on the screen as the minimum of the single slit pattern. Now, on the other side of this central max, how many maxima are there? Well, there's symmetry in these interference problems, so there are 4 that I did not bother to draw in here. So 4 to the left, 4 to the right of the central max. There's our 9th one. So there are 9 visible maxima inside the first central maximum of the single slit pattern. There are 2 central max being discussed here. There's an overall central max of the single slit pattern, and then there's a central maximum for the double slit pattern. And numbering these, 1, 2, 3, 4, I've also numbered the minima of the double slit pattern, 0, 1, 2, 3, and 4 is where the minimum of the double slit matches the position of the minimum of the single slit. So we have some equations that relate to interference with a double slit. The maxima can be located for the angle using an integer times the wavelength equals the separation of the two slits times the sine of theta, and that's a maximum. The values of m start at 0 and go 1, 2, 3 on up. So when we put a 0 in for m, to satisfy that, the angle has to be 0. That's our central maximum. When m is 1, our angle increases away from 0. When m is 2, we need a bigger theta. M is 3, bigger theta. M is 4, bigger theta, and so forth. The minima, we need destructive interference between the two sources. So now it's m plus a half times the wavelength equals separation times sine of theta. These are minima. And again, the m's are 0, 1, 2, 3. So if I use a 0, we'll be half wavelength out of phase for the light from the two slits. You should go to a textbook, look at the drawing for this. But that would be this minimum here. So m equals 0 gives us this first valley, this first destructive interference. What about the single slit pattern? Well, it's a little bit similar, but I'm going to use different letters here. N times lambda equals capital D, that's the slit width. That's the width of one slit, times sine of theta, again a minimum. And the values of n start at 1. I guess I didn't write that on here, but I'll do it now. Why doesn't n start at 0? Well, if I would put a 0 in here, that would make this theta be a 0, and there is no minimum of the single slit pattern at the same central position of the double slit pattern. They're both at a maximum here. So n starts at 1, and here is n equals 1. At the same place that m, the double slit pattern, is 4. This is the first single slit minimum, n is 1. All right, Well, how could we proceed? You notice that in this wording, the wavelength is not given. So it looks like we might have two unknowns here. And we do. Now, the wavelength is unknown, and up here, the slit separation, small d, that's unknown. So how do we proceed if we have two unknowns? We need a second equation. That's the purpose of the single slit equation, of course. So how can we, and I don't know theta either. I don't know this angle. So three unknowns. But not as bad a shape as you might think, because the thetas are the same. The thetas are the same. So in fact, I can solve for sine of theta for the appropriate equations here. I'll scoot this up just a little bit. So for the double slit, I use the minimum. We're not going to be using the max equation. This is a problem involving two minimums being located at the same angle. So sine of theta min for the double slit equation, it's n plus a half lambda over d. And for the single slit equation, sine of theta minimum is n lambda over d. And there I chose to write in the n's. So we can go a little further with this. These two thetas are the same. So I can equate, I'll go ahead and show you, n plus a half lambda over d is equal to n lambda over d. At this point, notice that the lambda factors can be canceled from both sides. And now we have n plus a half over d equals n over d. We take advantage that because there were 9 visible maxima inside this first maximum spread of the single slit pattern, that meant that 0, 1, 2, 3, m equals 4 is the appropriate m to use. And then, so 4.5 comes from 4 plus a half divided by d. And then 1 for the single slit pattern, n is 1. And we're told the width of each slit. So capital D is known, 0.0125. And that's probably a good technique here to write the units on that, 0.0125 centimeters. So we're going to be coming up with centimeters for the value of D. Go a little further, cross multiply both sides by D, multiply both sides by 0.0125. So 4.5 times 0.0125. The separation of the two slits is 0.05625 centimeters. In what way is this roughly correct? Well, the separation has to be bigger than the individual width. So 0.056, that is bigger than 0.0125. So at least from that basis, it succeeds. If you would divide these two numbers, 0.05625 divided by 0.0125, you get 4.5. Missing orders occur when these two numbers come up to be an integer when they're divided. So we're not in a missing order problem. We're doing okay. So again, working out this problem, saying that there were 9 maxima visible inside the first single slit overall maximum. We draw that out, and we count that there are out to the 4th maximum. And then I count out to what the m value would be. It's also a 4 to bring us to this position in the double slit minimum calculation. The thetas are the same, so we set the, could say sine theta min here equals d sine theta, small d sine theta equals capital D sine theta. But I've chose to solve for the, and what I just said was not correct. The sine theta minimum equals sine theta minimum for both equations. The d's are different. So I solve for sine theta minimum, should have stuck with what I did the first time. We get these two terms, I equate those, cancel off the wavelengths, and solve for small d, the separation. So I hope I didn't confuse you that last part there. Replay if necessary, ask your instructor if necessary, watch some more sample videos if necessary, and I have an annotated list of short physics lectures and the short example problems, physics.gpclements.com. If you have an astronomy interest, there's something a little similar, a little bit more widespread for the general public at astronomy.gpclements.com. And keep practicing your physics.